Hello everybody, my name is Wesley, and today we'll be discussing levitation using paramagnetism. Now we know what you're thinking. You're probably thinking, what the heck is paramagnetism? Well, before I get into that, let's discuss a couple of qualifications that we need to achieve levitation. There are three things we need. First is lift. For lift, we have an equation. It's P mag equals B squared divided by 2 times mu naught. And over on the right hand side, we have a little translation. So P mag is the force per unit area in pascals. B is the magnetic field just above a superconductor in Teslas. And mu naught is of the permeability of a vacuum. And it's an official number. It's 4 pi times 10 to the negative 7. Now, the other thing we need is stability. Now, this might be a little confusing, but stability doesn't actually have an equation that I was able to find. But there is this equation that I wrote, which is the minimum criteria for diamagnetic levitation. And I'll explain what diamagnetism is in a little bit. So you have the magnetic field times the rate of change of a magnetic field along a vertical axis equal to the permeability of free space times the density of material times gravity divided by the magnetic susceptibility. So with those three things, we can achieve levitation. Now, to answer the big question, what is paramagnetism and diamagnetism? Well, to start, we have ferromagnetism, which we're all familiar with. It has a north and south pole, it's the strongest, and it's composed of iron. Now, it will also like poles repel, opposite poles attract. Then we have paramagnetism, which is weaker than ferromagnetism. The material is composed of unpaired electrons, and because of that, it's attracted to both ends of a magnet. Okay. And then we have diamagnetism, which is the weakest of the three. It is composed of paired electrons, and because of those paired electrons, it's repelled by both ends of a magnet. Like I said, it's the weakest of the three. There's actually something within diamagnetism called superconductors. They're also known as perfect diamagnets. And the strongest of the superconductors is the element bismuth. You can find that in the periodic table. And we'll talk more about diamagnetism later in this video. Alright, now for paramagnetic levitation. We have Earnshaws Theorem, which says a collection of point charges can't be maintained in a stable stationary equilibrium configuration solely by the electrostatic interaction of the charges. Translation proves that paramagnetism is impossible for a static system to stably levitate against gravity, aka you can't levitate using paramagnetism. It's not stable enough. And if you could think about, you have a magnet just sitting here. If I were to place another magnet on top, it would flip over and shoot off. So because of that, it's not stable enough to support levitation, except for liquid oxygen. Now we have our hybridization orbitals with our sigma and pi bonds. You can see at the top there are 2 unpaired electrons within the pi antibonding orbital. So because of that, liquid oxygen is affected by paramagnetism, and it will actually levitate between 2 closely spaced magnets. But we actually want to be able to levitate things, so we come to diamagnetism. So we have, going back to our superconductors or perfect diamagnets, they're actually not naturally attracted to magnets. So we have to supercool them to a specific temperature, what we call the critical temperature. And once we achieve that, a couple of interesting things happen. We have what's called the Meissner effect. So we have a metal track down at the bottom here, or magnets. And then we have magnetic fields, and we have our superconductor M black. Now what's happening with the Meissner effect is it's actually repelling the magnetic field. Okay, so we have that repulsion there. And then the third thing that happens is called flux pinning or quantum locking. Basically, there are imperfections in the material which allow the magnetic field to go inside or go through the superconductor, and they actually get trapped within the superconductor, locking it or pinning it in place. There's a really cool video I will introduce you to at the end of this presentation, and there's a really great demonstration of this flux pinning and superconductors. So, moving on, a couple applications. Number one is maglev trains. It is very energy efficient. It requires much less energy to use magnets to run a train than it does electricity or coal. There's no friction, and because of that, bullet trains in Japan, or maglev trains, whatever you want to call it, will reach 430 kilometers per hour or 270 miles per hour. So pretty fast. Magicians, if you're into magic, entertainment, they can use magnets for those purposes. And if you have artwork or something you like to put on display, make it a little stand out more, magnets can be great use for that as well. Alright, now I actually don't have, unfortunately, the resources to show you those demonstrations, liquid oxygen and superconductors, but if you go to these YouTube channels with their URL addresses, you can see examples of those. So we have the title of each video on the left and the URL on the right. So if you want to see a frog levitate using diamagnetism, just go to that first one. If you want to see that superconductor train, not necessarily a train, but that little puck on the track that I drew out, you can go to the second URL. And if you'd like to see oxygen levitate and a more explanation between the differences between paramagnetism and diamagnetism, you can go to that third URL. There's also a little sailboat, little makeshift sailboat the guy makes, and he uses bismuth to set sail. So, hope you enjoyed the presentation, and we'll see you later.